All right. Ladies and gentlemen, distinguished foundry leaders, industry partners, and honored guests, good afternoon. Hope you all had a good lunch and are now energetic for the last paper of the day. Our last speakers of the day are Mr. B. Chandra Reddy, Senior Application Engineer, and Mr. A. Elakkiyan, Application Engineer, Snam Alloys Private Limited. I now call upon Mr. Rajmohan Madhiyalagan, our Honorary Secretary, IIF Chennai Chapter, to introduce the speakers.
Good afternoon, everyone. It's my pleasure actually to introduce the next speaker of the day. We have two speakers. Mr. Chandra Reddy holds a M.Tech in Material Science and Technology from Central University of Tamil Nadu with nearly 3 years of specialized experience in manufacturing industry. He has developed a sharp focus on metallurgical analysis of both gray and ductile iron. Currently, he serves as a Senior Application Engineer at Snam Alloys R&D Center. The next speaker, Mr. Elakkiyan A, holds a Bachelor of Engineering in Metallurgical Engineering from Government College of Engineering, Salem. Currently, he serves as an Application Engineer at Snam Alloys R&D. They both work as a team to develop new products for process control and overall product performance in foundries, oversee and implement use of thermal analysis system in foundries, provide critical technical support and consultancy for inoculants, nodulants, and associated products to foundries. They also perform foundry defect analysis, helping the foundries to take the first step in solving the problems. Let us welcome Mr. Chandra Reddy and Elakkiyan. Thank you.
Thank you for introducing, sir. So good afternoon, everyone. I hope you all enjoyed the lunch. So first of all, I would like to thank my company, Snam Alloys, for giving me this opportunity to present, and also I would like to thank organizers of SOURECON 2026 for creating this opportunity. Today my topic is about solid solution strengthened ferritic grade ductile iron. So basically this is it's simply as we can say SSFDI. So the SSFDI was first introduced in early 1980s by Volvo Group to improve upon conventional cast iron grades. In this presentation, we can see how SSFDI has superior properties compared to conventional cast irons. So in this presentation, I am going to cover these topics: what is solid solution strengthening, what happens after solid solution strengthening, and how to produce solid strengthening ferritic grade ductile iron, and role of silicon in SSFDI, various grades of SSFDI, conventional grades versus solid strengthened grades of ductile iron, and applications of it, advantages of SSFDI, and we have conducted some experiments in our R&D to produce SSFDI. So I will explain the experimental data and outcomes of it. Finally, I will conclude with general guidelines to produce SSFDI based on the experimental data. So what is solid solution strengthening? Before that, let us understand what defines the strength of material. Basically, plastic deformation defines the strength of material, and plastic deformation depends on how dislocations move in a crystal lattice. If dislocations move easily in a crystal lattice, then the material is softer. If dislocations are blocked or difficult to move in a crystal lattice, then the material is stronger. So simply to strengthen the material, we need to block the dislocations in the crystal lattice. So for strengthening single phase metals, we have 3 different types of strengthening mechanisms. One is grain size reduction, solid solution alloying, and strain hardening. In grain size reduction, by reducing the size of grains, the grain boundaries will block the dislocation and helps to improve the strength of a material. In solid solution alloying, we will add an alloying element to a base metal so that this alloying element will create a distortion in the crystal lattice and block the dislocations. So finally, it will improve the strength of material. In strain hardening, we will physically deform the material so that dislocations will interact and block each other and improve the strength of material. So in both the cases of grain size reduction and strain hardening, we need to do one extra step after casting. But in case of solid solution strengthening, while producing casting itself, we can strengthen the material. So solid solution alloying. In solid solution alloying, we generally add atoms of alloying element to a base metal So this will dissolve in a crystal lattice and form a solid solution. Solid solution is classified into two types. One is substitutional solid solution. The other one is interstitial solid solution. So in substitutional solid solution, the solute atoms will replace solvent atoms and create a distortion in the crystal lattice. For example, sternic silver. Silver is a soft material, but when we alloy it with the copper metal, so this will increase the strength of the silver, and it can be used in applications like conventional jewelry and silverwares. For example, we can see in PPT left side we have that we can consider that blue color atoms are silver atoms and orange color atoms are copper atoms. So that these carbon atoms will copper atoms will replace the silver atoms and makes the material stronger. But in case of interstitial solid solutions, the solute atoms will occupy the interstitial sites, the gaps between the solvent atoms. For example, carbon occupies the interstitial sites of iron. For example, in steel and cast iron, you can see the carbon will occupy the interstitial sites and increase the mechanical properties. So generally, what happens after solid solution strengthening? In a simple way, we can say this after solid solution strengthening, the material becomes stronger by blocking the dislocation movements. For example, you people are know like caterpillar, right? Which is a starting stage of butterfly. So it slides one step at a time. So if you leave the caterpillar in a smooth place, so it will slide one step at a time and reach the destination fastly. So when we place some obstacle like stone or something, so it will for caterpillar it will be difficult to reach the destination, and so in a similar way we can see that in normal condition without alloying, the atoms in a crystal lattice easily slide over easily sliding by sacrificing the grains. But in case of solid strengthening conditions, these alloying atoms will act as an obstacle and create a disturbance in the crystal lattice, so that it will block the dislocations and make the material stronger. So how to produce solid solution strengthened ferritic grade ductile ion? So generally, to strengthen ductile ion, we use strengthening elements like silicon, phosphorus, manganese, copper, etc. But in case of producing a ferritic grade ductile ion, we are using silicon at the range of 3.2 to 4.3, depending upon the grade. Why silicon? Because silicon will promote the ferrite phase in a material. So it will help us to increase the mechanical properties by increasing the silicon percentage. So as the silicon percentage increases, the mechanical properties will increase, and also at constant silicon level, we can achieve fully ferritic matrix throughout the casting section thickness, independent of casting size or geometry of the casting. But other elements like phosphorus and manganese we cannot use because it can have harmful effect in ferritic grade ductile ion. So role of silicon in solid solution strengthened ferritic ductile ion. In FeSi alloys, the silicon will act as a substitutional solid solution. So silicon atoms will replace the iron atoms in BCC lattice, and carbon atoms will occupy the interstitial states in a ferritic solid solution. So as I told, mechanical properties are majorly influenced by silicon. With increasing silicon percentage, the mechanical properties will increase. Overall mechanical properties will increase. So as the silicon content increases, the ductile to brittle transition temperature also increases. The higher the silicon percentage, it will compress the perlite formation and promote ferrite formation and in a retracted transformation, and hence make the material stronger. So now various grades of solid solution strengthened ductile ion. As per EN standard, EN 1563, EN 1564 issued in 2012, we have three different grades of SSFDI, which is 450/18, 500/14 and 600/10. When we see SSFDI compared with conventional grades, we have with the same grade of conventional grade, when we compare with SSFDI, so we have increased in yield strength and elongation, and also the Brinell hardness number is also we can achieve with minimal variation in Brinell hardness number. So similarly, like conventional grade, conventional cast ions for SSFDI also we have some acceptance limit based on the casting section thickness. For section thicknesses up to 30 mm we have some limits to achieve mechanical properties, and casting section thicknesses from 30 mm to 60 mm we have some acceptance limit. Above 60 mm it should be agreed between the foundry and purchaser. So, the chemical composition as per EN standard 1563 as follows for different grades. The phosphorus and manganese which should it maintain in a constant addition rate throughout the different grade sizes. Phosphorus is 0.05 and manganese is 0.03 maximum, but by varying grade size the silicon percent also increases. And microstructural properties for SSFDA as per EN standard 1563, we need to maintain minimum 95% of ferrite phase and maximum of 5% of perlite is allowed. So, and also like 20% of compacted graphite ion is compacted graphite ion is allowed, and but rest it should be recommended to form type 5 or 6 grade nodule category as per established in EN standard ISO 9451. And also nodularity is also not mandatory of 80%. But we should achieve the mechanical properties. If we achieve the mechanical properties, nodularity is not mandatory of 80%. So when we compare the same grades of conventional grades and SSFDA grades, we can, as I told earlier, there will be increase in yield strength and elongation. So in this chart we can see comparison of yield strength for grades 450, 500 and 600. The yellow color identifies the conventional grades and blue color identifies the SSFDA. So we can see around 13 to 27% of increase in yield strength compared to conventional grades in SSFDA. So when we see the elongation, we can see almost three times higher when compared to conventional grades. For example, if you take a 600 grade, the elongation for common conventional ductile ion is only 3%. But in case of SSFDA, we have 10% of elongation in SSFDA. So when we see the hardness comparison, so we can able to achieve lower hardness, lower average hardness with minimal variation in SSFDA compared to conventional grades. In conventional grades, we have larger variation in Brinell hardness number. So when we see the microstructure of conventional grade ductile ion and SSFDA, so in SSFDA we can see fully ferritic matrix which help us to achieve homogeneous mechanical properties throughout the casting section, and it also help us in easy machinability, so which will finally help in improving the tool life. But in case of conventional ductile ion, we have perlitic and ferritic matrix, so it makes the material some brittle, and when compared to SSFDA, the machinability will be difficult in conventional ductile ion compared to SSFDA. Applications of SSFDA. So applications of SSFDA includes in the field of agriculture, automotive, wind energy. In agriculture, we have rear axle and steering knuckle, automotive, A-spring member and steering knuckle. In wind energy, we can see the bed plate. But why SSF? So SSF can replace forged part to a casting, and also by reducing weight, we can increase the mechanical properties. And one more thing is we can achieve homogeneous properties independent of casting thickness. Whether it's thinner casting or thicker section, we can achieve homogeneous properties throughout the casting, and it's also rupture free because of ferrite matrix. Advantages of SSFDA, as I discussed, it will increase the mechanical properties. We can see there is a 13 to 23% of increase in yield strength and almost 3 times higher in elongation, and it will have a uniform matrix distribution throughout the casting, and it's not sensitive to nodularity and carbide formation. So based on this data and literature survey, we have conducted experiments in our R&D to produce solid solution strengthened ferritic grade ductile ion. The grades produced are 600 by 10, 500 by 14, 450 by 18 by varying addition rates of FSM and inoculant. The following are the process details. So we have followed chemical composition as per the standards, and tapping temperature maintained around 1520 to 1540. And treatment method is Tundish cover sandwich treatment method. FSM we have used common grade 6 to 7% magnesium grade at the addition rate of 1.1 to 1.2. Inoculation is we have used barium based inoculant 0.45 to 0.55 in two different stages, one in treatment ladle and another is transfer ladle. We also added nickel based on the requirement from 0 to 2.2 to 0.25%. So the following samples castings were poured during trials for mechanical analysis. We have poured AFS, standard AFS coupon to check hardness and microstructure of casting, and also 1 inch Y black to check the tensile properties, tensile strength, yield strength and elongation. And we have poured a step block, two different step block, 20 mm step block, 80 mm step block, which consists of 5 mm thickness, 10 mm thickness, 20 mm thickness, 20 mm, 40 mm thickness and 80 mm thickness to check nodulity, nodule count and microstructure properties throughout the casting different section thicknesses. So as per the discussed parameters, we have conducted trials by varying different compositions, and from the trials the following addition rates and composition yield the best results. The addition rates are as follows. We have used magnesium 6811 at 1.2% and inoculant Hybecal we have used at 0.45% and nickel 0.2 to 0.25% we have used. So the following table shows the metallurgical and mechanical properties of 600/10 grade at different pouring time intervals. So in the table we can see the nodulity of we have achieved nodulity almost 90% and nodule count as per the standard, and also we have achieved all mechanical properties as per the standard. So the effect of nickel on mechanical properties. So when we try to produce 600/10 without nickel, we are unable to achieve mechanical properties such as tensile strength, yield strength, because because in this grade the silicon percentage is 4.3. If you go silicon percentage more than 4.3, so it may have tendency to form chunky graphite or segregation of alloying element in microstructure. So we can't increase the silicon to increase the mechanical properties like yield strength and tensile properties. So we have added nickel to increase the tensile strength without affecting the ferrite phase. So we have added 0.2% and we have achieved almost all mechanical properties as per the standards for 600/10 grade. Effect of silicon and microstructure. Here with the silicon percentage 4.4, we can see the microstructure of different cross section thicknesses 5 mm, 10 mm, 20 mm, 40 mm, 80 mm. In a thicker section we can see the starting the formation of a chunky graphite or degenerated graphite, so that we should control silicon within like 4.3. So similarly, we have tried to produce 500/14. From the trials, we have this combination give the best result. The combination as follows: Mg6811 at 1.15% and Hybecal at 0.5%. But when we try to produce 500/14 without nickel itself, we have achieved all mechanical properties. The table shows mechanical properties and metallurgical properties at different pouring time intervals. So we have achieved nodulity of minimum 90%, and also peer lead percentage is only 1% as per the AFS chart, and also we have achieved minimum tensile strength of 500 megapascal, and also hardness is also within the range. So when we try to produce 450/18, so this is the best combination. With 1.1% of magnesium and inoculant of 0.55%, we have achieved the mechanical properties and metallurgical properties as per the grade of 450/18. These are the mechanical and metallurgical properties at different pouring time intervals. So based on the experiments conducted, we tried to form a general guidelines to produce SSFDI and the chemical composition as follows mentioned in the table, and also addition rates and process parameters will vary according to the foundry practices. Here in our case we have maintained tapping temperature of 1520 and treatment method is Tandy-Scott treatment method, and FSM is we have used MG6811 and barium based ibical inoculant we have used. So for nickel, if we based on the grade requirement, we should add nickel. Any question?
Actually, foundry guys are very slow. You are too technical, you are going very, very fast. But you have not told me many things. One thing is this grade is very, very important going forward. Because earlier, what are the grades? We normally in automobile castings, they go for 11 mm, 12 mm wall thickness across the castings. Because of the yield strength is more, you can reduce minimum 12 to 15% you can reduce the wall thickness and get the things done. And I personally done for 2 components and it is running successfully. And this is going to be the order of the day because this grade has developed in Germany 10 years ago. During past 10 years, nobody knows in India. But recently it has started coming. It is going to take place. Please try to put in your foundry. And this grade is going to give the weight reduction. That is, you have seen the morning chief guest was talking about lightweight castings. Now, this is one of the phenomena we can think of going for light. Okay, but beautiful subject. It is a 2-hour subject. You are finished in a half an hour. I don't know how much it has gone into the brain, but it is too good. I think you can circulate the hard copy if you have.
Thank you, sir.
Anyhow, Mr. Prem Kumar has vouched for your product. People can blindly follow it up.
Any other questions, gentlemen? All right. So I now call upon Mr. K. Varadarajan, sir, our organizing committee chairman, SOURECON, to felicitate our speakers with the Angastram and memento.